Today we're going to learn a technique called trig substitution, and we are actually not going to compute any integrals right away, but we're going to learn how this process works. This is kind of an interesting kind of substitution. Before we jump into what trig substitution is, let's compare these three integrals here. So we notice these all look very similar. They have a radical with the same expression underneath it. And they have an X somewhere in there. So you might think like, well, we could probably use the same technique for all three of these. If we started working on these, we could try U substitution. Usually we would pick the stuff under the radical for our U. So our du over dx is 50x, which gives us du over 50x is dx. So if we started rewriting these, like this first one, I'd have x over root u times du over 50x. The 50 or the x's are in different spots. One's in a numerator, one's in the denominator, so they'll cancel each other out. We get an integral that just has u in it, so u substitution works great in this first example. Similarly, in the second example, we're going to have x root u du over 50x, sorry. The x's again are going to cancel each other out, so u substitution works great there. The last example, we're going to have a problem because the x, all of the x's are in the denominator. So the x's are not going to cancel out. They're just going to multiply together to give us something like 50x squared du, which doesn't really help matters. So this last example is going to end up needing something called trig substitution. Trig substitution is interesting because we start out with a problem that doesn't have any trig in it, and we introduce trig to the problem. It's going to work best in problems where we have radicals, and so cases like this third one are going to be kind of the typical kind of example where we use trig substitution. But before we actually do an integral with trig substitution, let's learn what the substitution looks like and how it simplifies radicals for us, because that's really why it's useful. It makes the radicals nicer. It gets rid of the square roots. Okay, so this little table here is going to be handy for you. So what you're going to do here to get started with trig substitution is you're going to look at what's inside the radical, what's under the square root. So if the format is something like a number minus x squared, so this could be something like 16 minus x squared, then we're going to use the substitution where x is equal to sine theta. And this trig identity in the middle is going to become handy. And we'll see how this works in just a second. I'm just going to give you the brief rundown here. Okay, so this next one, if I have something like x squared plus a number, then I'm going to make the substitution where x is tan theta. And finally, if I have x squared minus a number, so like x squared minus 16, I'm going to use secant for my substitution. And these will all work if we have a coefficient with the x. So if I have like a 4x squared in there, 5x squared, 25x squared, whatever you want. So we can have extra numbers in front of the x, and then we can still do the substitution. So let's just jump in and see how this works. So if I look at this first example, I have x squared plus a number, x squared plus 4. So that's in this format. So we're going to use this middle line. So it looks like I should make my x equal to tangent theta. And my goal is to use this identity that tan squared plus 1 is secant squared. So what we're going to have to do here is we're going to have to be a little bit careful. All of these, we're going to have some coefficient in front of the tangent or the sine or the secant. And we just have to figure out what that coefficient is going to be. And the way that we figure out what that coefficient is by looking at whatever number is out here and whatever number is in front of the x squared. So there's nothing in front of the x squared right now. So I'm going to treat that as like a 1 in front of the x squared. And there's a 4 here. So what we're going to do is we're going to take the square root of both of those numbers and put them out front. So I'm going to take the square root of 4 and the square root of 1. And this is how I'm going to write them. So what would happen in general is if I have like ax squared plus b, then my substitution, I'm going to get the square root of b over the square root of a. The thing that's associated in front of the x is going in the denominator because we want it to cancel out eventually. Okay, so let's see. So this is really just 2 tangent theta. Okay, so now let's make this substitution. When I substitute this back in over here, I'm going to get 2 tangent theta, that whole thing squared, plus 4. So when I square that, that's 4 tangent squared theta plus 4. Okay, the reason that I had put that 2 or that square root of 4 in the numerator is because now I can pull a 4 out of everything, factor a 4 out, so I'm left with tangent squared theta plus 1. Okay, now this is where our trig identity comes into play, as we've boiled this down where I can use the trig identity. So tan squared theta plus 1 is secant squared, so we get 4 secant squared theta. Now the beauty of doing all of this is that I have gotten this down to something where I can get rid of the square roots now. So this is going to be 2 secant theta. We actually put absolute values with this, although when we integrate, we usually don't include the absolute values. The absolute values are here because of the fact that when we take the square root of something squared, the inside has to be, we need the whole thing to be positive, but secant could be negative. Okay, so kind of to summarize what we did here, we used this table to figure out what substitution we needed. We had to figure out what those coefficients were going to be. Once we did that substitution, we should be able to use the trig identity to boil this down to something where we can get rid of the radical. Okay, so kind of a lot, but we'll get more comfortable with this over the next couple of class days and eventually use this to actually integrate. So let's see what happens in these other examples. So this next one is of the format a number minus x squared. So we're going to be working with this first line. So I'm going to pick my x to be sine theta. I have to figure out the coefficient in front. The coefficient with the x is a 7. So I'm going to put a square root of 7 in my denominator. We're putting this in the denominator again because we want it to cancel out with the 7 that's in front of the x. And then the number out front is just a 1, so I'll put a root 1 out front. Okay, so my x is going to be 1 over root 7 sine theta, which looks kind of messy, but is not too bad. Okay, so we're going to make that substitution. So when I make that substitution, I'm going to get 1 minus that whole thing squared. Whoops, I forgot my 7 from here. Don't do that. Don't forget the coefficient. 7 times 1 over root 7 sine theta squared. Okay, so that's going to give me radical 1 minus 7 times 1 over 7 sine squared theta when I square everything. And so now this is why I put that 7 or that root 7 in the denominators, that the 7s are going to cancel each other out. So I'm left with root 1 minus sine squared theta. And if we go back, that's our trig identity now in the middle. 1 minus sine squared is cosine squared. And this is always the case. When you do these substitutions, you should always be able to end up with something of this format. If you're not, then you have made a mistake in your substitution or picked the wrong thing to substitute. Okay, so that was cosine squared. So we get square root cosine squared theta, which is just cosine theta. Again, we're going to put the absolute values there. Okay, but we won't put the absolute values when we do the integrals. Okay. This last one is an integral. I'm not actually going to calculate the integral, but I'm going to rewrite everything in here. And we'll talk in class about how to actually do the integral because they can sometimes get messy even after doing the substitution, which is sad, but okay. Okay, so let's look at this one. This is a number squared, nope, an x squared minus a number. So we're in this last scenario here again, or not again, we're in this last scenario. So we're going to make x secant theta. And we need to figure out what my coefficient is going to be. So in the denominator, I'm going to put the thing associated with the x. So I'm going to put a square root of 25, which is just 5. In my numerator, I'm going to put the square root of 4, which is 2. Okay, so this is my substitution. Since this is an actual integral, I'm going to need to figure out what dx is as well. So dx d theta, the derivative of secant is secant tangent. And so if I multiplied both sides by d theta, I get dx is just this times d theta. Okay, so I can rewrite my integral now. So there's a lot to rewrite here. So I'm going to have a square root of 25 times 2/5 secant theta squared minus 4 all over x. I'm going to replace x with this guy again, 2/5 secant theta, and then my dx I'll replace with all of this, 2/5 secant theta tan theta d theta. Okay. I notice a few things are going to cancel out right away. The 2/5 secants cancel out, which is nice. But the key is that the reason that we did the substitution was to get rid of the square root. So let's work on that piece. So when I square this, I'm going to get, let me just do a side up here. When I square that, I'll get 4/25 secant squared theta. All of that still times 25 minus 4 still. When I multiply the 25s together, they'll go away. So I'm going to be left with 4 secant squared theta minus 4. I'm just being lazy and writing this kind of on the side up here. So now I can pull a 4 out of all that. So I'm left with secant squared theta minus 1. And it's okay if you do that like as an aside because it's messy to rewrite all the integrals. We still have the tangent theta d theta out here from our dx. Okay, now we're going to go back and use our trig identity. Secant squared minus 1 is tangent squared. So this is an integral of the square root of 4 tan squared theta. Still, we have that tangent to outside from our dx. Okay, square root here is going to give me 2 tangent theta, and then we still have that tangent theta at the end. So we could write that as 2 tan squared theta. Then we would have to keep integrating from here. So like I said, we'll do the actual integration in class. For now, we want to just get practice rewriting those radicals so that we can get rid of the square root.